Testing. Okay, today's lecture is going to be a nice application of geometrical ideas for the last 3 or 4 lectures, and it's entitled Calculus of Variations. And there's quite a lot of material in here, and what I'd like to do is just walk through some of the background material and show some of the practical problems. And where it ties into the course very nicely is in this dialogue of the Bernoulli brothers with Isaac Newton. And one of the original calculus of variation problems was posed as a problem to Newton in 1696, and he was the first one to correctly formulate it and solve it. So what I'd like to do today is look at the background of the calculus of variations. And this is a link that comes from Math World. And what we're doing is trying to minimize the integral. Now, let me just try to motivate where you might want to minimize an integral. So the calculus of variations comes historically from problems like the following. So you might have a physical quantity. Suppose you might have a light ray going from, say, point 1 to point 2. Now we know in a vacuum the straight line will minimize the distance between these two between these 2 points. But what if we have a medium? Put it in blue here. So what if we have a medium in here where the properties are not homogeneous, so the velocity or the refraction index actually varies. So the light ray may actually wander around and go like something like this. So we know the light ray will take the shortest path, or at least the shortest time. Now, what's the time between paths? Well, if we look at the velocity is the derivative of the length on this path with respect to time. And that means dt is equal to ds over v. So the integral of dt will be the integral of ds over v. And so I want to calculate the time between point 1 and point 2, say. Point 1 and point 2. So what I'm trying to do is minimize the total time. And that should determine a path. Because after all, if you take alternate paths, if you take, say, a path that, say, is close by but is different, the total time should be longer on these dotted lines than the minimum path. Okay, so it's not the shortest length, the geodesic, it's the shortest time, because the velocity can be a function of position. So what we're trying to do is minimize an integral with fixed endpoints. Now, if you knew the velocity as a function of position, x and y, you could write this as ds is the square root of dx squared plus y squared over the velocity as a function of x and y. And let's see, there is no d here. And you could rewrite that as the following: the integral of factoring out of dx, I could write this as 1 plus dy dx squared divided by v of x. So if I knew the velocity as a function of x for every point in this media, I could integrate from x1 to x2, and this is the total time. So what I want to do is find the y, and this, after all, is a function of y of x. So what I'd like to do is minimize t of y. So minimize over all y's, which are, say, continuous, t of y. Okay, so this problem is what generates calculus of variations. Historically, they came from a physical problem, say the path that a light ray would take in a medium with variable refraction index, and you're trying to minimize this quantity. Now, minimizing an integral will give you, analogous to when you minimize a function of a single variable, what do we know? When we minimize, say, y equals a function of x, we know that if we look at the graph of it, at the location of the minimum and the maximum, you have a horizontal tangent. So we should look at a critical point where f prime equals 0. That we know, or it's possibly undefined. So f prime undefined or endpoint. So this is the set of points to look for a local minimum or a local maximum. Now, when we're minimizing an integral, we're going to get the analogous of this differential f prime equals 0 condition. And for the calculus of variations, this condition is going to be called the Euler-Lagrange. So let's look at the problem. Minimize I of y, an integral of y, which is a fixed integral from a to b of a function of x, y, and y prime. Now, it certainly is a general function, right? I'm just integrating an arbitrary function of x, y, and y prime between, and this is obviously x equals a and x equals b. Now, what does the minimization actually imply? This implies if y is a minimum, or let's call it y star is a minimum, it clearly means that if I calculate the value of this integral at y star, it's less than or equal to any other function if y doesn't equal y star, right? Because if this were violated, if y star, integral of y star was bigger than I of y, then there would be another minimum. So the minimum forces this to happen. Another way of saying this is that, alternatively, the integral of y star plus epsilon eta of x is bigger than I of y star. That's another way of saying it, because this is just another function. For any eta, positive or negative, and for any eta, epsilon and eta. Now, if we expand this, we'll get our conditions. So let's actually copy this. And go and start off with another. Okay, so we'll look at this condition here. What we have now is that the integral of f from a to b of x, y plus epsilon times another function, and y prime plus epsilon eta prime is bigger than or equal to the integral of a to b f of x, y, and y prime. because that's exactly the integral of y plus epsilon eta. Now, just use a Taylor series here. That's the obvious thing to try. How do we do a Taylor series of a function of more than one variable? Well, we just write this as f of x, y, y prime, plus df dy, evaluated at x, y, y prime, times eta epsilon, plus then you'll have a df squared, dy squared term, times epsilon squared, eta squared, over 2, plus some higher order terms. That's just this argument here. Plus you'll get, of course, df dy prime times eta prime epsilon, plus some higher order terms, df dy prime squared, eta squared, times epsilon over 2, plus higher order terms, and then you'll get some mixed terms like, for example, d squared f dy dy prime, eta squared, or epsilon squared eta prime, plus all this stuff. Okay, so there's my Taylor series here. Now I can write this integral, therefore, as the integral of f, x, and y prime plus a term involving epsilon. Then I have from A to B, let's B there. Then I have df dy times eta plus df dy prime times eta prime. That's from, let me circle it, that's from this term and this term. And then I have an order epsilon squared term times this big complicated integral and higher terms. Okay, now what's the condition that this be bigger than or equal to I, x, y, and y prime? Well, if you look at it, and let's copy this, oops, don't want to delete it, I want to just copy it. Let's look at this here. Oops, here. Going to move this to where I can view it. Okay, so this cancels out, obviously. This first term cancels with this. And so you get a term involving epsilon. These are not there. You get a term involving epsilon and a term involving epsilon squared bigger than 0. So you're going to get an equation of the following form. You're going to get epsilon times something plus epsilon squared times something plus higher order stuff bigger than or equal to 0. Now, this implies two things. First of all, this term multiplying epsilon squared better be positive. In other words, if it's a quadratic that's positive, it better be convex up. And a little more subtly, this term better be 0. Because this is supposed to be true for epsilon bigger than 0 or less than 0, both cases. So if this term were not 0, I could multiply it by an epsilon of a different sign, And that would give me a term that would be negative because the epsilon would dominate the epsilon squared. So the only way this inequality can hold true is if the linear term vanishes. So that's the classic result that the first variation of the integral vanishes. So this term right here is called the first variation. That equals 0. The second term is called the second variation, and that must be positive definite. Okay, so if you look at the first variation, we conclude with the integral from a to b, this term, df dy times eta of x plus df dy prime, eta prime of x, equals 0. Now, that's the so-called Euler-Lagrange equations. It's analogous to f prime equals 0 for a function of a single variable. Now, this is supposed to give you conditions on y. How does it do that? Well, in order to see that, I'm going to integrate the second term by parts. Okay, so let's copy all of that. Okay, so let's consider this, the Euler-Lagrange equations, and let's integrate by parts. Now, what that's going to do is convert an eta prime to an eta. So I'm going to say that df dy prime times eta prime is really the derivative of df dy prime times eta, because that's the first times the derivative of the second, but then I have to subtract d by dx, df dy prime times eta. Okay, so that's an identity. So in particular, I can write this as the total derivative minus this. So I will get integral from a to b, eta x times df dy. Now look at this term here. This becomes the total derivative of this minus eta times the derivative d by dx of partial f with respect to y prime. Now I also have this term here, so I have a boundary term, df dy prime, eta of x between x equals 0 or a and x equals b. Now, one thing I neglected to say, if I'm trying to find the minimum of this integral, is I'm going to require that y be fixed at the endpoints. So eta of x vanishes at both endpoints. Now, if those are 0, this boundary term is gone, and I have this term equals 0. Now look at this term. This says, for arbitrary functions eta, the product of eta times this bracketed quantity must be 0. Now suppose this term was smooth enough to be continuous, which we will assume. If this is continuous, suppose that the graph of that bracketed term were positive over some interval between a and b. A and b. If this term were positive, I could multiply it by an eta that were positive and that was 0 everywhere else. So the product of this eta times this thing, which is positive on the support of eta, would be, the product would be positive, and this couldn't happen. So the only way this product can be 0 for all choices of eta is if this bracketed quantity equals 0. So in fact, the Euler-Lagrange conditions are not just in an integral form. I've reduced them to a point-wise differential equation. So the Euler-Lagrange equations become the following. The derivative of f with respect to y minus d by dx of the derivative of f with respect to y prime equals 0. That's the Euler-Lagrange equations. These are a necessary condition for the integral from a to b of f of x, y, y prime dx to be a minimum. These are a necessary condition as long as f and y and everything else is smooth enough. Okay, so what we've done, and this is very nice, is we've reduced this very complicated problem of minimizing an integral to a more or less standard first-order partial differential equation. Now, if f is a function of y and y prime, these derivatives will be non-zero, so I'm going to get a very complicated function of x, y, and y prime. So this is really a differential equation. It's an ordinary differential equation, nonlinear, for y of x. And with the two boundary conditions that y of a is prescribed, call it capital A, and y of b is some constant. So it's two boundary conditions and then a second order differential equation. Now the reason why it's second order is suppose f depended linearly on y prime, so f looked like y prime, then the derivative of y prime would be a y double prime. So this is like a second order differential equation. Okay, now let's go back to some history. The Bernoulli brothers, and actually there are four of them here, there was a father and an uncle and then the two sons. They posed the following problem. It's called the brachistochrome problem. Now the brachistochrome comes from two words in the Greek. The first one is brachistos, that's this word here, and chronos, meaning time. So brachistos means shortest, chronos time. So the brachistochrome problem is find the path of the shortest time between 2 points. So here's the very famous brachistochrome problem. And it's analogous to the roller coaster problem, which is find the curve that gets you from point A to point B in the shortest amount of time, because that will give you the most feeling of acceleration on a roller coaster. So shortest time. So all we have to do is identify this function. Well, we know what the time is. The time is the integral from P1 to P2 of dt. P1 to P2, that's really dy, or ds rather, over the velocity. Why is that? Because v is ds over dt. So obviously ds is v dt, hold it. No, dt is ds over v, that's the way I want it. Okay, now, by conservation of energy, look at a point here on this. This has kinetic energy equal to 1/2 the mass times the velocity squared. So if you start off here at time 0 and you're rocketing down here, at some point you're going to have gravitational potential energy, which depends on your height y, and you're going to have a scalar velocity v, which gives you kinetic energy 1/2 mv squared. And the potential energy looks like mg, mass times the gravity, times the height. Okay, so with a little bit of argument, you can show that the integral ds, just like before, was the square root of 1 plus dy dx squared times dx, that's ds. And what's v? Well, v is like, if you balance the kinetic energy and the potential energy, m's cancel, you get v as the square root of 2gy. So we're going to put 2gy square root here. Now this is going to go from x1 to x2 now, change of integral. So now my function f of x, y, and y prime is going to be 1 plus y prime squared to the 1/2 power, 2gy to the minus 1/2 power. And that immediately gives you the Euler-Lagrange equations, df dy minus d by dx df dy prime equals 0. Now I could take this function f, plug it into here, set it equal to 0, and solve for it, but it turns out that there's a much easier solution. Now if you go down here, this is just the derivation that we went through here. So here's the functional that I'm minimizing. Here's f. Here's the Euler-Lagrange equations. But it turns out that in the special case where f does not depend on x, there's a Beltrami identity that comes from a separate calculation from this link here. If you go through here, you come up with the following identity, equation number 8. If you use that in this particular case, that's equation number 8, you end up with the following curve, that 1 plus dy dx squared times y equals a constant. And that turns out to be solvable in terms of parametric equations of theta, and it turns out to be given as a cycloid. Now a cycloid, if you've ever seen the spirograph, as they say here, it's just the locus of a point on the rim of a circle of radius A rolling along a straight line. No, I did not cache this particular page, so it's coming in slowly. Here we go. There's a picture of it. That's a cycloid. It's a point on the rim doing this. So if I were to turn it down and take a piece of the arc, so if I take a circle and roll it around, it will then it'll look like this. Now if I turned it upside down and then take a piece like this will be a solution of the Brachistocone problem. Now I emphasize this is not a half circle. This is a more complicated circle, but it's a cycloid. So if you want to know what shape a roller coaster is, if you're starting out here and go down to this point, this is part of the cycloid. Let's see, the parametric equations of a cycloid are given here. So in Cartesian coordinates, it looks like this. In parametric form, it looks like that. And this is x in terms of y. So it's a rather complicated function. So it's best actually done parametrically. Because of these linear terms plus sines and cosines, it's difficult to eliminate theta. Well, I guess what you do here is you can solve for theta in terms of y and then plug in for x in terms of y. So you can get x as a function of y pretty easily, but not y as a function of x. That's more complicated. So I'll mention that as a brief. You can solve for x equal x of y. It's pretty complicated. But parametric is just fine. Okay, so that turns out to have a closed form solution, and in fact, it was posed to Newton back in 1696. After all, he was doing this just after he invented the calculus with Leibniz. So he took it up as a challenge, and I believe it took him less than 24 hours to actually get posed the problem, formulate it, and then solve it. So that was pretty good. There's another related problem called the Todochrone problem. And this is the following, is can you define a curve so that no matter where you are on this curve, it takes you the same time to get down to the bottom? So in other words, if you start very slow, it's shallow, so it takes a little smaller time. If you start up here, you go up faster, and you get to the same point at the bottom in the same amount of time, no matter which way you let it go. Now, interestingly enough, this function actually made it into Moby-Dick. So if you look, I'm not sure, I didn't check the page reference, but he says here that indirectly struck by the remarkable fact that in geometry, all bodies gliding along a cycloid, my soapstone, for example, will descend from any point in precisely the same amount of time. So Herman Melville knew about the Todochrone, or this cycloid, and worked it into the great white whale there, Moby Dick. Now, they actually made this into a pendulum, and here are the parametric equations. But you can formulate this as a problem of equal time, and that again gives you a problem in the calculus of variations. Now, we've already discussed the Euler-Lagrange equations. Another problem that is related to this historically was the plateau problem. Now, the plateau problem, I mean, it's not plateau in the sense of being flat, it's a fellow named Plateau. The problem is that of finding a minimal surface with prescribed boundaries and without any corners or cusps. So even with caching, it's taking a amount of time. And so let's actually draw a picture here. So suppose I have a coat hanger, and I dip it in soap solution, and I have another smaller coat hanger down here. Then the soap film is going to make a bubble between these, and so there's a boundary here and a boundary here. Now these could actually be in the plane or in 3 dimensions. So, and this is intended to be a soap bubble. And it stretches out, and if you pull it too far, it'll kink together and break. But if it's close enough together, and these can actually be planar curves or actually curves in R3. But you can imagine that if you just take two coat hangers and dip them in a soap bubble and pull them apart, you're going to get a soap bubble connecting it. Now this has a very nice property, and this is a minimal surface. And a minimal surface is exactly a surface with Gauss curvature 0. The reason why it has curvature, Gauss curvature 0, is that there is, and you can see pretty much that this is like a saddle point surface because you have curvature one direction this way and curvature the other direction this way. So this has Gauss curvature 0, and because there's no net force. The curvature is related to the force, and if there's no net force on the surface, because the surface isn't moving, that the equilibrium condition says that the Gauss curvature is 0. So there's no net force. Actually, there is a force, but the force of surface tension is being balanced out by other forces on the surface. Because if a surface is not moving, the net force obviously has to be 0, which says the Gauss curvature is 0. Okay. Now, the other thing you might think of as a minimal surface, which is the surface of a sphere, is not a minimal surface, because the Gauss curvature is 1 over r squared, which is obviously positive, and this does not have Gauss curvature 0. Now, this is a closed surface where the surface tension is balancing out the pressure inside of the bubble. Okay, so a sphere is not a minimal surface. At least not in the sense that of having curvature 0. It's the surface with minimal surface area for enclosed volume, but that's not the same as being a minimal surface having a net sum. So I can write down the equations of a minimal surface, and that is, it just minimizes the surface area. And if you write down the equations, you'll end up with the Gauss curvature equaling 0. So the Euler-Lagrange equations of the integral of dA, which is the surface area in 3 dimensions, if I minimize that, the Euler-Lagrange equations imply Gauss curvature equaling 0. So if you look at this, for example, imagine soap film putting in a if you had a soap film inside a box, so view these as the soap films here. So they go from the side, they connect in the center, and then they go down like this. So that's an actual problem. And you can actually get bubbles which have square edges. So the minimal surface solution for this is, in fact, a surface with a flat part in the center here, and these are all flat. Now, prescribing a surface with curvature 0 with given boundaries, which is the same as finding the formula for a soap bubble, is again a problem in calculus of variations, because you have to minimize an integral, which is the surface area. So that's Plateau's problem. Now, there are known to be surfaces, minimal surfaces without boundary. For example, a plane does not have a boundary. So finding minimal surfaces without a singularity and without a boundary is fairly difficult. There are only a few of them known. I believe there's 3. There's the helicoid. Let's see, we'll click on the minimal surface link there. So, the minimal surface is a surface with mean curvature 0 that satisfies given boundary conditions at the end. satisfying this equation, which is the Euler-Lagrange equation, which is Gauss curvature equals 0. Now it says later on here, Euler proved that if you have a surface with Gauss curvature 0, it's planar if and only if it's locally saddle-shaped. Now, whether the surfaces have singularities or not, that means kind of cusps or corners, was not known. And then later on they showed that you could not have a minimal surface with a singularity. And then this is an interesting paragraph. The only known boundaryless, that means there's no wires, it's just an infinite, boundaryless surface containing no self-intersections, the bubbles don't cross each other. Our finite topology was the catenoid, helicoid, and the plane. And then recently they discovered another one which is much more complex. So it talks a little bit about those. Now, it's also interesting that the calculus of variations made it to Hilbert's list of problems in 1900. In fact, it was his last problem. Hilbert's 23rd problem was a mathematical extension or rigorous justification of the calculus of variations. So let's go back up here. Up and up and up and up. Okay, so further developments of the methods of calculus of variations is number 23 on Hilbert's problem list. So that's a historical. Now in physics, this is where it really gets interesting. The calculus of variations and minimization plays a very natural role. So for example, let me just do an example of solving a problem, just so it doesn't look too abstract. You can actually show that the shortest distance between 2 points is a straight line if you define distance as the square root of dx squared plus dy squared. So if you look at the distance between point 1 and point 2 of ds, so that's square root of dx squared plus dy squared. If you factor out a dx, this is 1 plus y prime of x squared, square root dx, going from x1 to x2. So this is point x1, x2, y1 to x2, y2. Okay. So this is my function here, f, of x, y, and y prime. And what are the Euler-Lagrange equations? It's df dy minus derivative df dy prime. So Euler-Lagrange equations give you this. Now what is df dy? Df dy is 0. Because you can't find, the function doesn't depend on y, so this is 0. So that's an actual simplification. So this gives me d by dx of, and what is the derivative of this with respect to y prime? Well, it's 1/2, 1 plus y prime squared to the minus 1/2 times 2 y prime. Now, there's no y double prime on here because I'm not integrating, differentiating with respect to x. I'm differentiating with respect to y prime. But if you look at this, this says the derivative of this equals 0. So what's inside is a constant. So this says that this term is a constant. So y prime over square root of 1 plus y prime squared is a constant. Call it C1. Now, if I multiply by both sides and square it, I will get y prime squared equals C1 squared times 1 plus y prime squared. If I solve this for y prime, I'll have a 1 minus C1 squared on the left. So this is c1 squared over 1 minus c1 squared. So y prime is just a constant. Call it constant 2. And if the derivative is a constant, then y is linear. So c2x plus c3. So this is the graph of a straight line. So the shortest distance between these 2 points is in fact a straight line. Okay, well that's obvious. What isn't obvious is if you take a different measure for arc length, suppose I measure the distance now as ds as some function of x and y plus 2f dx dy plus g times dy squared, where e, f, and g are functions of x and y, etc. Then the minimal surface is minimize square root of e times dx squared plus 2f dx dy plus g dy squared. And this is equal to square root of e plus 2f y prime plus g y prime squared dx. So this is my f here. And so the Euler-Lagrange equations are now d by dy of this big thing, e plus 2f y prime plus g y prime squared minus d by dx d by dy prime of that big thing. And that can be a real mess, and it's not clear that the surface is going to be a straight line. In fact, if you have like a light path, it could wander around. In fact, it might even be multiple solutions. You could have 2 different paths like this. Now, this is an aside, and this was something that really fascinated me when I first heard about it, is you might ask yourself the following: how does light know to take the shortest path? So in other words, if you shine a light here, it sends out photons here. And how does it know that it ends up at B and it takes the shortest path? So, I mean, can light somehow look ahead and figure out where it's going to go and say, well, if I went here or went here, it would take me a little bit less time than over here, so I'll go this way and I'll just keep marching along? Does it look ahead somehow and say, yeah, that's the shortest path? It's sort of like you going on a map and without knowing the map, figuring out what the shortest path between College Station and San Francisco is, without knowing the map, and just by knowing like which way to put your foot next. Now, this really was puzzling, at least to me. How does light know how to take the shortest path or the shortest time? Actually, this is the shortest time. Well, in a sense, it doesn't. And this was a fellow named Richard Feynman, who's a physicist. He actually said, well, this idea of light sampling the paths is not all that far from reality. In other words, if you look at a path here, and you look at, and light, after all, is now not just a photon, it's a wave function, which is a solution of something called Schrödinger's equation, but it has an amplitude and a phase. So light particles now have amplitude and phase. And it just miraculously, or maybe not miraculously, it turns out that if you look at all possible paths that connect A and B, and you look at the wave function that along this path, and you integrate the wave functions along all paths, an amazing thing happens. Basically, the wave functions cancel out. In other words, this will be a little bit out of phase of that, and the only place where there won't be any cancellation out is right on this surface here. So the reason why the light wave travels here is because, in one sense, it really has taken all possible paths between A and B, and all of the ones have actually canceled out, leave in amplitude and phase, except for the one path that actually ends up being the path that the light takes. Okay, so this is actually a very interesting idea. And it says that the idea of minimization and optimization and calculus of variations are very much a part of physics. This. So these are also known as T-diagrams. You may know Richard Feynman as the fellow who put the O-rings in the ice water and showed that from the original space shuttle disaster that the O-rings could dramatically contract under cold conditions. Okay. Now, there is an approach to physics that relies very much on the ideas of calculus variations and minimization. So let me just do a little aside on the calculus of variations type ideas in physics. We know that there are various conservation laws. What are some of them? Well, we know conservation of mass, right? This says, unless you have a nuclear reaction, in chemistry of standard reactions involving atomic particles, you cannot make or create or destroy atoms, so the number of atoms are always going to be a constant. The number of molecules may change because of atomic, but the total mass is going to be the same. You also have conservation of momentum, mass times velocity. And actually there are two kinds of momentum, linear and angular. And there's conservation of energy. And then you may have also conservation of charge, conservation of polarity, conservation of spin number, conservation of symmetry, conservation, a whole bunch of stuff. What a conservation law says is that something remains constant in time. So if I take the derivative in time of something, I get 0. That's what a conservation law says. Well, there's also, if I look at energy, conservation of energy, this says that the time rate of change of the kinetic energy plus potential energy equals 0. So if T is the kinetic energy, it's the energy from motion, and U is the potential, this says that the sum of potential and kinetic energy, which is called E, remains constant, ignoring friction and things like this. So when you have a conservative force and the momentum gives you velocity, gives you a potential energy and kinetic energy, which is constant. There is something called the Lagrangian, which is a related idea, which is not the sum, but it's the difference of T and E. So it's the kinetic energy minus the potential. Now, this actually has the following. One can show that if you integrate the Lagrangian between T1 and T2, it's minimized. So the equations of motion are given by minimizing the Lagrangian. Now, this is a calculus of variations problem, right? Because I can write the Lagrangian as a function of position and velocity. So let Q be the position. So if Q is the position and Q prime is the velocity, then the potential energy is usually a function of position, and kinetic energy is a function of velocity. So this is equal to T1, T2, Lagrange of Q, Q dot. And what are the equations of motion for this? Equations of motion, well, I guess there could be a T in there. This says the Euler-Lagrange equations say that the derivative with respect to Q of L minus the time derivative of the derivative with respect to Q dot of L equals 0. So that's exactly the Euler-Lagrange equations. Now I claim these are the same thing as the laws of motion from Newton's laws of motion. So let's take a particular case. Let's let the kinetic energy be 1/2 mv squared, which is of course 1/2 m q dot squared. And let's let U be conservative potential. And I'm going to assume that it's conservative. Now, conservative is just a fancy name for meaning that you can actually get a force as a gradient of a potential. So that is, there is an F, which is the gradient of a potential, and that's a force. Okay, so what is the Lagrangian? It's T 1/2 mq squared minus the potential energy U, which is a function of Q. Now, what is the derivative of L with respect to Q? The derivative of L with respect to Q, not Q prime, so this doesn't depend on Q, so that's 0, is minus the derivative of U with respect to Q, which is F. It's a force. And what is the derivative of L with respect to Q dot? It's 1/2 mq dot times, well, 1/2 m 2q dot. So it's m times q dot. So if I put these two together into the Euler-Lagrange equations, in other words, put this into here, I'm going to just get Newton's laws of motion. I'm going to get the derivative of L with respect to Q, which is F, minus the derivative of dl dq dot, which is mq, equals 0. So this says the derivative of the momentum is equal to the force. So that's Newton's law. Newton's second law of motion. Okay, so Newton's laws of motion are completely equivalent to minimizing this integral of L. Now this is called the action, and this principle in physics is called least action principle. That is, things will move according to the principle that the action is minimized. So that's how the calculus of variations comes into physics, is you can formulate the action as the integral of the Lagrangian, and you can actually derive the equations of motion by requiring that this certain integral be minimized. There's another formulation of mechanics called Hamiltonian mechanics, which I won't get into. Now, I've actually given some references in case this isn't familiar. Most of this is out of the Wolfram, Eric Weinstein's encyclopedia that they acquired. So these are references on the web to calculus of variations. There's also a nice little HTML called the Easy Calculus of Variations. So if you want to do like calculus of variations in 20 minutes, you can read this reference. There's Maple worksheets, actually. You can download and explore calculus of variations. So, for example, the trajectory near a black hole, an application of Lagrangian mechanics, etc. That's kind of a nice one. There's a journal of calculus of variations that's put out by Springer Verlag, which you can look through old articles and preprints on. There's also a university in Pisa, Italy, which has tons and tons of PDF files, preprints dating back to 1995 of calculus of variations and minimal surfaces. And then finally, you can read a little bit about the Bernoulli saga going from 1654 to 1782. They were around quite a bit. There was really kind of a wild, let me just see if I can find one reference here that explains how incredibly wild this family was. This is a reference to Johann Bernoulli, and specifically down here it says, the Brachistochrone problem was solved by himself, Newton, Leibniz, L'Hopital, and his older brother Jacob. At first, Johann found an incorrect proof, and then tried to substitute Jacob's proof for his own, which is kind of wild. And also, like it says, one of their sons got a particular mathematical prize or position that they wanted, so they kicked him out of the house, and it was just kind of an incredible mathematical family there. Okay, so this ends today's talk on the calculus of variations and introduction. On the next lecture on Thursday before spring break, there won't be any lectures for the week next week after spring break for the distance students. Will be off. But lecture 15 will be on calculus of variations part 2, and what I want to do is just to go through a little bit more survey of this idea of minimization in physics and applied math, and also again in this idea of the role that one mathematician proposing a problem like the Brachistochrone problem to Newton and having that other person solve it and develop a mathematical theory, how that pushed forward mathematics tremendously in the 1700s and 1800s. Okay, so that'll end